Any questions about anything you can think of? Okay, so we're solving exponential equations in 9.6 and we're solving logarithmic equations. So they've got equations with variables in the exponents such as 3 raised to the x is equal to 20 and 2 raised to the 5x is equal to 64 are called exponential equations. We've talked about that. Those where the same base is on both sides of the equation or where the base can be made to the same on the both sides of the equation are going to be one type of exponential equation that we are going to solve. If you look at this one, you can see that this base is a 2 and this base is also a 2. This base is a 2. This is not obviously a 2, but I can make that be a 2 because 64 is 2 raised to what power? You might have to think about that. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So 2 to the 1, 2, 3, 4, 5, 6 power. So I can write 64 as a base of 2. And then we've got those where the base can't be made the same on both sides of the equation. So this base is a 3, and there's absolutely nothing I can do to 20 that would make the base be a 3. Okay, so those are the two type of equations that we're going to look at, exponential equations that we're going to look at solving. So this very first one says steps for solving exponential equations with the same base. So the first thing you want to do is determine if the numbers can be written using the same base. If so, you're going to go to step 2. If not, stop and use the steps for solving an exponential equation with different bases. So we're going to rewrite the problem using the same base, use the properties of exponents to simplify the problem. Once the bases are the same, drop the bases and set the exponents equal to each other, and then finish by isolating the variable, solving for x. Okay, so what does all that mean? First thing I'm doing is checking to see if my bases are the same here. And they are. They're both 2 raised to the 4x and 2 raised to the 12th. If they are the same, then you can just get rid of them, because if they are the same, then 4x should be equal to 12. And we know how to solve this. We would just divide by 4 and x would be equal to 3. Okay, so if you go back and check that, if you did a check on that and you plugged in 3 right here for x, you would get 2 to the 4 times 3 is equal to 2 to the 12th. Is that true? Yeah, because this is 2 to the 12th is equal to 2 to the 12th. So it's true. When the bases are the same, those are the easiest type of problems to work because you just drop the bases. So in other words, this is a 5 for my base and this is a 5 for my base. So I'm writing them again so that whenever you're making notes, you can read your notes, I guess. But since my bases are exactly the same, I can just get rid of those and say, well, then 2x must be equal to x plus 6. We know how to solve this type of equation. We can't have x's on both sides, so we would move one of the x's to the other side. So 2x, take away an x, would just be 1x. And 1x would be equal to 6. So x is 6. We could plug it back in up here to check and see if it would be, if that's true. Does this work when x is 6? So all I've done is plug in a 6 where I saw an x. Well, that's going to get me 5 to the 12th is equal to 5 to the 12th. So that's good, right? Okay. So when the bases are the same, those problems are extremely easy to solve. So when they're not the same, okay, like the next problem, they're not the same. We want them to be the same. If at all possible, we want to try to get the bases to be the same. So I'm looking at this problem right here, and this base is a 2. And this base is not a 2, okay? But if I can get it to be a 2, it will make my life be a lot easier. So is there a way that I can change 8 to be 2 to something? Exactly, right? 8 is 2 times 2 times 2. So I could change 8 to be 2 to the 3rd. And when I change it to be 2 to the third, now we have the same basis. So that means that we can just say, okay, well, 5x is equal to 3. We solve for x by dividing by 5, and so x would be 3/5. Okay, and so we could check our work by plugging in 3/5 up there where 2 to the 5x would be 2 to the 5 times 3x. And since we're saying x is 3/5, then this would be 2 to the 5 times 3/5 would end up being 2 to the third. And that's true. 2 to the third is 8. So we can always go back and check and make sure that we're doing the right thing. These are not the same basis. One of them is 4, and then the other thing is just 16. I would like them to be the same basis. So is there any way that I could get 16 to be 4 to something? I could, right? Because 16 is 4 times 4. So it can be 4 to the second, which means I can drop the bases and get 3x minus 5 is equal to 2. And so we would have 3x is equal to 7, divide by 3 on both sides. So x would end up being 7/3. We could always go back and plug that into x 7/3 and make sure that it's equal to 16. Well, 3 times 7/3 is going to be 7. So 7 minus 5 would be 2. And that's true. Checks out. It works. So the first thing you want, the first kind of equation that you, when you're solving these, you really, really, really want the basis to be the same. You want to work at that if at all possible. You want to get the basis the same. Questions about any of that stuff? So when you have something that has an exponent that has a different base, okay, so you're following these same steps. You're going to determine if the numbers can be written using the same base. If so, do that, get them to be the same base. If not, then you're going to take the common logarithm or natural logarithm of each side. Okay, so really the only time you would want to use a natural logarithm is if you're working with an e. Okay, because e goes with a natural logarithm. You're going to use properties of logarithms to rewrite the problem. You're going to divide each side by the logarithm and use a calculator to find the decimal approximation. And you're going to finish solving the problem by getting the variable by itself. Okay, so here I'm looking at this. This is one of those where my base right here is 3. There is nothing that I can think of that I can do to 20 that would make it be 3 to some power. Okay, so I have a little bit of a problem with that. So the next thing I want to do is I want to take the log of each side. So we're going to say we want to take the log of 3 to the x, and we want to take the log of 20. I've just taken the log of both sides. This would be log, and then what would be our little subscript down here? There's nothing there. 10 always if it's logarithm, right? It's always 10 if there's nothing there. Okay. So I'm trying to figure out what x is. So it's saying, okay, well, now you need to use your properties of logarithms. And during the last class, we talked about this a bunch, that we could take this x, if it's an exponent, and we can move it to the front, and we can write this x times the log of 3. So that's all I've done, because I really can't figure out what x is if it stays an exponent. So that's the whole purpose of taking that logarithm, so I can move it down. Okay, after this is not complicated because I can get x by itself. It's x times the log of 3. And the way that you get rid of a multiplication is you would divide by the log of 3 on both sides. So these cancel out because the log of 3 divided by the log of 3 is just 1. And on this side, you would have to use your calculator, and you would just you can just use the first row and do the log of 20. that log will work. You don't have to type in the base of 10 because it's assumed that it's the base of 10. So the log of 20 divided by the log of 3. And I am getting 2.72683, and it keeps going. It kind of depends on what it's asking you to round to. If we typed in our calculator just to kind of check and see if we got this close, if I say 3 raised to the 2.77683, because that's what it's saying here, it should be close to 20. Mine is telling me that it is 21.129. So it depends on where you're rounding, I guess. Okay. But it's not going to be exact because we did have to round. Is everybody okay with that? Okay. So it doesn't matter which one you use, but it would be better to use what here? Because we're working with an E. If you're working with an E, it's better to use the natural log. So the natural log of E to the negative T power is equal to the natural log of 0.04. Okay. There's that property that says that if you're working with logarithms and it's an exponent, you can move that exponent down and you would have negative T times the natural log of E is equal to the natural log of 0.04. I'm going to try to stay consistent because I don't want to confuse people, but you should recognize that what the natural log of E is. What is that? 1, right? Okay, it is 1. And so at this point, I would just say, well, negative T is equal to the natural log of 0.04. You're not going to get it wrong if you just do the steps we were doing though. So the natural log of E, because it is, just remind you from Friday, because if you've got a base E and these things are the same, then that's going to be 1. But I just need to get T by itself. So it would be okay if I just go, okay, I need to get rid of the negative. So I'm going to go ahead and divide by a negative natural log of E, which is really just dividing by a -1. But your calculator will do that part for you. So the natural log of 0.04 divided by negative natural log of E. And natural log is on that first row, right below the log button. It is that what y'all are coming up with? Because the natural log of 0.04 is a negative number when you take that. And then when you divide by -1, that's what you're going to get. So it kind of depends on what it tells you to round to. Is everybody okay with this? So when you can't get the logs to be this, or when you can't get the bases to be the same, you're going to take the log of both sides. Okay, so here's another one. My base here is really is just the E, because that's the part that's raised to the 8T. Okay, so the first thing I'm going to do on this problem is I am going to get rid of this 5 times this, because this 5 is not raised to the 8T power. Does that make sense? I need to get it down to just whatever the base is raised to that exponent. So I'm going to divide both sides by 5 so I can get that to be gone. And I can just have, okay, my exponent, I'm sorry, my E raised to the 8T by itself. So 2,500 divided by 5 is going to be 500. We're working with an E. I don't think there's ever going to be a way I can get 500 to be E to some power. Okay, so I need to do what here? take the natural log, because we're working with E, of both sides of my equal sign. There's a property that says I can move the exponent in the front of the natural log after that. That helps me. I'm going to use these same steps because I don't want to confuse everybody, but you should recognize that the natural log of E is just what? 1, right? The natural log of E is 1. But our calculator will handle that for us. So really all I want left on this left side of my equal sign is the T. So I'm going to divide by the 8 and I'm going to divide by the natural log of E on both sides. Because the 8s will cancel, the natural logs will cancel. So I'm just left with T is equal to whatever the natural log of 500 divided by 8 times 1, but you can still type it in that way. So the natural log of 500 divided by 8 times 1 is 0.776826. It just keeps going. Okay. What about this one? Do we have it down to just the base and the exponent? No. So the base is E and it's raised to the 0.09t. So we've got to get rid of that 1000. You don't take the natural log until you just have it down to the base and the exponent. Because if you do it at this point, it's not going to help you. You need to get rid of this 1000 by dividing both sides by 1000 first. So 5,000 divided by 1,000 is 5, and 1,000 divided by 1,000, that cancels out, and I just have E to the 0.09t. This is a natural log, so we're working with E, so I'm going to take the natural log of both sides. I'm going to move my 0.09t down in front. The natural log of E is just 1, but I'm going to divide by that, and I'm going to divide by 0.09 because I want those things. All I want left on this side is the T. So that means I need to do the same thing on the right side. So we're going to get the natural log of 5 divided by 0.09 times the natural log of E, which is just 1. 17.88264. It just keeps going. Questions about that stuff? If the base is different and you can't get it to be the same, you're going to take the natural log if it's an E, and you're just going to take the regular log if it's not, if it's any other number. Okay. So the last type of problems that you would solve using this are equations that contain variables in logarithmic expressions. So the log base 2 of x is equal to 4, and the natural log of x minus 2 is equal to 7. So the way that you do this is when there's only one log expression. Okay, so we've got one side of this is written as a logarithm, the other side is not. Convert the logarithmic equation to an exponential equation and then solve it, which we've been working a whole lot with this. This was the thing where we said, if you have the log base 2 of x equals 4, always write the log in the front, and then you go to the first number, skip over the variable or whatever that second number is, and come back to it. So that would be 2 to the 4th is equal to x. That's how you write it in exponential form. Right? That's how you go back and forth. So this one would be in exponential form, 2 to the 4th is equal to x. Well, then that means that x is whatever 2 to the 4th is, 16. You could absolutely check it using your log function in your calculator. That how do you get to the log where you can type in that the base is 2? Do y'all remember? Go to math. And then you scroll down to log base. And you can plug it in and check it from there. And so I am actually going to do that real quick, just to remind you guys where that log base thing is. So if we go to math, it'll let me type in, okay, I've got the base of 2. And we just figured out that we thought it was 16. And it's giving me the answer of 4, which is what it's supposed to be, right? So I could check my work there. Just remind you where that is. It's under math. It says log base. Same thing here. So you're always going to make sure your log is written first. Pick your first number, skip over the second thing, which would be our x, and then come back to it. So we're saying 3 to the negative 2 is supposed to be x. If you type in 3 to the negative 2 in your calculator, it's probably going to give you a decimal, and you can do math enter to make it not a decimal. But if you have a negative exponent, we talked about the fact that what that means is that you've got 1 over 3 squared is what this is equal to, which is 1/9, and that's what x would be, 1/9. So if we go to our calculator, let's look at how we can make it look right. So if we say, what is 3 to the negative 2? See, it gave me a decimal. I don't want that. Most of the time, the My Math Labs, they're going to want the exact answer. So I can go, can you make that be a fraction? So I hit math and hit enter, and it tells me it's 1/9. So you can, the calculator will do that, go back and forth from decimals to fractions if it'll change for you. I just hit math and typed in and hit enter because I wanted it to be a fraction. Okay, so I can check that. Here we go. This one's a little bit different because usually I said, oh, start with, I'm gonna stretch this out just a little bit so I can make sure I'm explaining. I said, start with this first thing, but there's no thing there. If it's a log, what is that? So you're going to say, oh, go 10, skip over the middle, which go to the last thing, which is the 3, and then come back to this is equal to 8 minus 7x. So if there's no subscript down there, you're going to have to actually write it down. If it's a 10, if it's a log, it's going to be a 10. And if it's a natural log, it's going to be e. So to solve this problem, I'm going to actually have to figure out what 10 to the third is. I'm going to have to calculate that because I can't change this to 10 raised to something. So 10 times 10 times 10 is 1,000. Then I could subtract 8, which is 992. Divide both sides by -7. And x is equal to 992 divided by -7. So I am getting -141.71, and it keeps going. Okay, is everybody good with that? I don't see a base here, but I know this is, I don't see my little subscript down here, but I know this is an e because it's natural log of x plus 5 is equal to 3. So I'm going to write it as an exponent. I'm going to say e to the third is equal to x plus 5. I know right now that if I type in e to the third in my calculator, it's going to give me some decimal. So I like to go ahead and say, okay, subtract 5 and get, I like to do this all in one step just so that my answer is as exact as possible. So I don't write down some random decimal and then subtract 5. Does that make sense? So I just go to the calculator. E, if you want to raise e to the power, that's right above the ln button. So second e to the third minus 5. And I'm going to get 15.0855. And it keeps going. ... that last little thing that says the calculator is always helpful when solving equations. We haven't done this a lot in here, but we can go ahead and look at this. It might help some of you guys. But it says for any equation, put the left side of the equation in y1 and the right side of the equation in y2, and then find the intersection, okay? And if you get really stuck, that might be something you want to do. So let's just look at this last problem. Ln of x plus 5 equals 3. So in y1, we're going to type in ln of x plus 5. In y2, we're going to type in 3. So I'm going to y equals, typing in the ln of natural log of x plus 5. And it was supposed to be equal to 3. And so I'm typing that into y2. Okay. Then I'm going to hit graph. I just want to look at it. So I'm trying to find where these two things intersect. It looks like it's going to intersect off of this graph, but we can go second calc, find the intersection, because the intersection is supposed to be the answer. So I'm going to enter. And I do want it to guess. It tells you hit enter 3 times. And it said no. Let me go back and look what I did. Second. I'm sorry. Yeah, it's gonna make, I was hoping that it wouldn't make me move the window over, because some of you all struggle with that, but I think you can tell that it's gonna cross somewhere down here. In fact, we just did this problem. What did we get for the answer? So we got the answer was 0.0855.
15.
Oh, I was fixing to say, that would have been on this graph. Okay, so 15. So we need at least to go over to where our window, change our X maximum. So I need to go above 15, maybe 20. Okay, so I can hit graph, and then I can see it's intersecting down here at 15 something, right? So then we could go second calc. That's going to be one of the limitations about using this. You have to actually be able to see it. So first curve, enter, second curve, enter. Where do they intersect? And it's there. That's the answer we came up with, that 15.0855. But you actually have to be able to see where they intersect to use that. So that is kind of a drawback. As long as you can work your window, it's good. So there's another way you can work these. Okay.